Hello and welcome to my YouTube channel Petro Intelligence. My name is Shahid Khan and I am a chemical engineer. I have prepared a training course on instruments in refineries and chemical plants which will be beneficial for those who are working in oil and gas refineries and chemical plants. After completing this course, you will be able to describe the basic instruments used in the process industry, identify and draw standard instrument symbols, describe temperature, pressure, flow, and level measurement techniques, identify the elements of a control loop, describe cascaded control, compare automatic and manual control, explain the importance of the operating percentage on a control valve. Before starting the course, let us have a look at key terms. Absolute pressure, PSIA, is the pressure above a perfect vacuum or zero pressure. Actuator is a device that controls the position of the flow control element on a control valve by automatically adjusting the position of the valve stem. Automatic control allows a control loop to utilize all 5 elements and work to match the set point. Bellows pressure element is a corrugated metal tube that contracts and expands in response to pressure changes. Board-mounted equipment are instruments, gauges, or controllers that are mounted in a control room. Borden tube is a hook-shaped, thin-walled tube that expands and contracts in response to pressure changes and is attached to a mechanical linkage that moves a pointer. Cascade control is a term used to describe how one control loop controls or overrides the instructions of another control loop in order to achieve a desired set point. Control loop is a collection of instruments that work together to automatically control a process. The basic elements of a control loop include primary element or sensor, transmitter, controller, transducer, and final control element. These devices are typically connected with electric lines and a pneumatic line to operate the valve. Control valve is an automated valve used to regulate and throttle flow, typically provides the final control element of a control loop. Controller is an instrument used to compare a process variable with a set point and initiate a change to return the process to a set point if a variance exists. Differential pressure, DP, cell measures the difference in pressure between 2 points. Distributed control system, DCS, is a computer-based system that controls and monitors process variables. Electric actuated valve is a valve that utilizes electricity to actuate or move the flow control device. An example of this type of valve is a solenoid. Field-mounted equipment instruments or controllers that are mounted near the equipment in the field. Final control element is the device in a control loop that actually adjusts the process, typically a control valve. Gain is the ratio of the output signal from the controller to the error signal. Gauge pressure, PSIG, is the pressure above atmospheric pressure. 0 is equivalent to approximately 14.7 psi at sea level. Hydraulic actuated valves utilize a hydraulic actuator to position the flow control element. Internal designs include piston or vane. Indicator gauge is an instrument used to show the value of process variables such as pressure, level, temperature, and flow. Interlock is a device that prevents damage to equipment and personnel by stopping or preventing the start of certain equipment if a preset condition has not been met. Manometer is a device used to measure pressure or vacuum. Manual control allows the controller to open the control valve and set it at a predetermined percent. Permissive is a special type of interlock that controls a set of conditions that must be satisfied before a piece of equipment can be started. Pneumatic actuated valves utilize air to actuate the flow control element. Internal designs may be piston, vane, or diaphragm. Primary element and sensor are the first element of a control loop. Primary elements and sensors come in a variety of shapes and designs depending on whether they are to be used with pressure, temperature, level, flow, or analytical control loops. An example of a temperature element is a thermocouple. A flow control primary element is a turbine meter or orifice plate. A level element is a displacer. A pressure element is a Borden tube. Many different types of primary elements or sensor care are used in the chemical processing industry. Process instrumentation are devices that control and monitor process variables, transmitters, controllers, transducers, primary elements, and sensors. Programmable Logic Controller, PLC, is a simple, standalone, programmable computer that could be used to control a specific process or be networked with other PLCs to control a larger operation. PLCs are inexpensive, flexible, provide reliable control, and are easy to troubleshoot. Resistance Temperature Detector, RTD, is a device used to measure temperature changes by changes in electrical resistance in a platinum or nickel wire. Rotometer is a flow meter that allows fluid to move through a clear tube that has a ball or float in it. Numbers on the side of the tube indicate flow rate. Set point is desired value of a process variable. Sight glass gauge is a level measurement device consisting of a transparent tube and gauge attached to a vessel that allows an operator to see the corresponding liquid level. Thermocouple is a temperature measuring device composed of dissimilar metals that are connected at one end. Heat applied to the connected ends causes the generation of voltage that corresponds to the temperature change, which is indicated on a temperature scale. Thermowell is a chamber installed in vessels or piping to hold thermocouples and RTDs. Transducer is a device used to convert one form of energy into another, typically electric to pneumatic or vice versa. Transmitter is a device used to sense a process variable such as pressure, temperature, composition, or flow and produce a signal that is sent to a controller, recorder, or indicator. Vacuum is any pressure below atmospheric pressure. Vacuum pressure is pressure below zero gauge, often expressed in inches of mercury. Basic instruments. Automatic control is the foundation for efficient continuous flow processes. At one time, operators controlled processes manually. This type of process was valve-intensive. It required the technician to open and close valves in piping lineups manually. Modern advances in instrumentation have made it possible for industrial manufacturers to automate their processes. To a process operator, this means that an instrument or computer can control the opening, closing, and positioning of valves, start and stop equipment, measure process variables, and respond automatically. This automation enables a single process technician to monitor and control large, complex process networks from a single control center. Basic process instrumentation as shown in picture includes gauges, transmitters, controllers, transducers, primary elements and sensors, computers, control valves, and other final control elements. Each instrument can be represented by a symbol as shown in picture. Temperature measurement. Process technicians are required to closely monitor the temperatures of process streams. When heat energy is applied to an area, molecular activity increases, and energy is transferred from molecule to molecule. As this process occurs, pressure and temperature increase in an enclosed environment, materials expand, and density changes. Temperature is defined as the degree of hotness or coldness of an object or environment. Two commonly used scales are Fahrenheit and Celsius. Fahrenheit scales operate by using 32 degrees Fahrenheit as the freezing point for water and 212 degrees Fahrenheit as the boiling point of water. Celsius uses 0 degrees Celsius as the freezing point of water and 100 degrees Celsius as the boiling point of water. Process operators use Fahrenheit and Celsius thermometers to measure temperature. Local temperature indicators usually contain a bimetallic strip that differentially expands with increasing temperature, causing a deflection that is correlated with temperature. Bimetallic thermometers, thermocouples, can range from -300 degrees to 800 degrees Fahrenheit. Another familiar type of thermometer has a primary element or sensor that consists of a filled thermal bulb and capillary tubing, resistance bulb, or thermocouple. In industry, mercury is not used in thermal bulbs or capillary tubing. The most common temperature measuring devices used in the chemical processing industry are thermoelectric. Thermoelectric temperature measuring devices. Thermoelectric temperature measuring devices come in two types: resistance temperature detectors, RTDs, and thermocouples. Both RTDs and thermocouples are held in a thermowell, a chamber installed in vessels or piping. An RTD is a thermoelectric temperature measuring device composed of a small platinum or nickel wire encased in a rugged metal tube as shown in picture. The electrical resistance in the wire is influenced by changes in temperature. Temperature changes in an RTD are sensed by an electronic circuit and directed to a temperature indicator. Thermocouples are composed of two different types of metal as shown in picture. A thermocouple is designed to convert heat into electricity. When heat is applied to the connected ends of a thermocouple, a low-level current is generated. The higher the temperature, the greater the current generated. Electric current is detected easily by the associated electronic circuit and is converted to a corresponding temperature scale. Thermocouples come in several types. J-type and K-type thermocouples are the most common. Type K is preferred for higher temperature measurements. Temperature control loop. This picture is a simple layout for a temperature control loop. In large, fired heaters, a temperature measurement is taken at the furnace or from the exiting charge. The primary sensors used to detect temperature are thermocouples or RTDs, often called temperature elements. Temperature elements are linked to transmitters, that is, devices that sense a process variable and produce a signal that is sent to a controller, recorder, or indicator. A 4 to 20 mA signal is sent to a controller that compares it with a set point, that is, the desired value of a process variable. Controllers are designed to initiate a change to return a process to its set point if a variance exists. Controllers may be located in the field near the equipment or in a remote location. The controller sends an electric signal to a transducer, which is typically located near the valve to eliminate process lag. The transducer converts the electric signal to a pneumatic signal of 3 to 15 psi. The control valve in picture opens and closes depending upon the signal. Reducing or increasing fuel flow to the burners controls temperature. Pressure measurement. Pressure is an important variable that must be carefully monitored and controlled in an industrial environment. Pressure is often defined as force per unit area, that is, the amount of force exerted by fluid on the equipment in which it is contained. In physics, the term pressure usually is applied to a fluid, which, in this context, can mean either a gas or liquid. Pressure is measured in pounds per square inch, (psi), in the English system, kilograms per square meter in the metric system, and newtons, (N), per square meter, or pascals (Pa) in the system of international units. A newton is 1 kilogram per square second. Two of the most common types of pressure are atmospheric and hydrostatic. Atmospheric pressure is the force exerted on the Earth by the weight of the gases that surround it. At sea level, atmospheric pressure is about 14.7 psi or 1.013 pascals. This pressure decreases with altitude because of the reduced height, and therefore weight, of gas. Hydrostatic pressure is the pressure exerted on a contained liquid and is determined by the depth of the liquid. Even a novice swimmer is acquainted with the pressure differences at the surface of the water and the bottom of the pool. This pressure difference is what causes your ears to pop as you swim to the bottom of a 10-foot swimming pool, hydrostatic, or drive over a high mountain range in Colorado, atmospheric. Blaise Pascal, a French scientist, discovered in the 1650s that pressure in fluids is transmitted equally to all distances and in all directions. From this discovery, Pascal formulated what is known as Pascal's law, which states that in a fluid at rest in a closed container, a pressure change in one part is transmitted without loss to every portion of the fluid and to the container. Fluids act this way because the molecules move about freely. The distance between molecules depends on whether they are in solid, liquid, or gas states. Molecules in gases are much farther apart than they are in solids. Also in the 1650s, an Irish scientist, Robert Boyle, developed laws that describe the relation of pressure to the volume of a gas. Boyle's law states that at constant temperature, the pressure of a gas varies inversely with its volume as shown in picture. The higher the gas pressure, the closer the gas molecules are and the smaller the volume they occupy. Under ordinary conditions, gas volumes decrease by half when the pressure doubles. Liquids and solids also respond to pressure increases, but in much smaller proportions than gases. Liquids and solids are generally considered non-compressible. The converse of Boyle's law is that pressure can affect temperature. It also affects level and flow rate. Pressure changes the boiling point of chemicals, their reaction rates, and the speed at which fluids flow through piping. These changes can affect product quality, so many instruments, or pressure elements, have been invented and designed to monitor and control pressure. This picture shows some pressure elements. Pressure gauges. There are three commonly used pressure scales in the manufacturing environment: gauge, absolute, and vacuum. The most commonly used pressure scale is the gauge scale, on which values are expressed in pounds per square inch gauge, PSIG. The gauge scale starts with atmospheric pressure, 14.7 psi, as 0 and moves up the pressure scale. The absolute pressure scale starts with a perfect vacuum as 0. Values are expressed in pounds per square inch absolute, PSIA. The absolute scale takes into account atmospheric pressure. To convert from gauge pressure to absolute, add 14.7 pounds to the PSIG value. To convert from absolute pressure to gauge, subtract 14.7 pounds from the PSIA value. Be cautious and do not stand directly in front of the gauge when opening the valve that admits pressure to the gauge. Once the valve has been opened, stand directly in front of the gauge face to take the gauge reading. If you position yourself to the left or right of the gauge face, an effect known as parallax occurs. Parallax is an optical illusion that shifts the gauge face reading left or right of actual. The space between the pointer and the face of the gauge causes the parallax problem. A PSIG gauge cannot be used with system processes that operate under a vacuum. Negative pressures cause the primary elements to contract beyond design limits. If a PSIG gauge accidentally encounters a vacuum, the reading scale is compromised low. Vacuum gauges overcome this problem. They are designed to operate at less than atmospheric pressure. Vacuum gauges express pressure in inches of mercury. Vacuum is considered to be anything below atmospheric pressure. Compound gauges can indicate both vacuum and gauge pressure readings. Manometer. A manometer is a device that can be used to measure pressure or vacuum. It operates under the hydrostatic pressure principle that a column of water of a given volume always exerts a specific force. The liquid level of the water indicates the pressure. There are three basic types of manometers. A U-tube manometer measures pressure in units of inches of water. Add the inches displaced on the inlet leg plus the inches above the zero on the outlet leg. On a well manometer, read the scale directly. The scale of an inclined manometer is also read directly, but the scale is expanded to make it easier to read small changes. Primary pressure elements. Primary pressure elements are the specific part of a pressure instrument designed to sense changes in pressure and convert it to mechanical motion. Pressure elements are connected to mechanical linkages and scale indicators. The higher the pressure, the greater the movement by the mechanical linkage. Bellows pressure. A bellows pressure element consists of an accordion-type bellows, a spring that resists expansion of the bellows, a pressure inlet, a mechanical linkage, and a pointer as shown in picture. This type of device can be used to measure a variety of pressures. During operation, a bellows pressure element admits flow into the bellows. As the bellows expands, tension on the spring increases, and the mechanical linkage moves. This movement operates the pointer on the gauge. If the pressure is reduced, the spring forces the bellows back to its original position. Borden tubes. The most common type of pressure element is a Borden tube. Bordens come in a variety of shapes and designs. The most common are the C-type, helical type, and spiral type. C-type Borden tubes are named for their C-shaped, hollow pressure element as shown in picture. C-type Bordens are composed of a C-shaped hollow tube, a pressure inlet attached to one end of the tube, a mechanical linkage attached to the top of the Borden tube, and a pointer. During operation, the tube expands and contracts in response to pressure changes. This process is sometimes referred to as elastic deformation. This expansion moves the mechanical linkage and pointer. Bordens measure a wide variety of pressures, including vacuum. Helical and spiral type Bordens operate the same way the C-type Borden does. The main difference is in the actual shape of the pressure element. In an automatic control system, a spiral type Borden can be connected to a transmitter. As the spiral element responds to pressure changes, the transmitter sends a signal to the controller, which sends a signal to the control valve. Diaphragm capsule. Pressure element. The third type of pressure element is a diaphragm. Diaphragms come in two basic types: diaphragm capsule pressure element and slack diaphragm pressure element. The metallic diaphragm capsule pressure element consists of a metal cup covered by a flexible metal plate, a pressure inlet line to the cup, a mechanical linkage, and a pointer. Diaphragm capsule pressure elements are designed to measure small pressure changes. During operation, the dome of the cup flexes up or down. Because this movement is transferred to the pointer proportionally, a little movement on the dome can equal a lot of travel on the pointer. The key components of a slack diaphragm pressure element as shown in picture are a flexible diaphragm attached to a spring, a pressure inlet, a mechanical linkage, and a pointer. Slack diaphragm pressure elements are designed to operate under very low pressures, 0 to 0.5 psi. Pressure transmitter. A pressure transmitter as shown in picture uses a pressure element to sense pressure and sends a signal to a controller or recorder. Pressure transmitters use all of the primary pressure elements just discussed. Linkage movement allows the transmitter to transmit a signal that is representative of the pressure to a controller or recorder. A controller opens or closes control valves depending on the signal it receives from the transmitter. Pressure control loop. Pressure control loop design has the same elements as temperature, level, and flow control loops. The one area that changes consistently is the first, primary elements and sensors. Pressure control loops use devices to detect and respond to pressure changes. These primary elements are typically expansion-type devices. This picture includes a pressure transmitter, controller, transducer, and control valve. Fluid flow measurement. Fluids flow through a series of pipes, valves, pumps, and vessels. Knowing and controlling the flow rate of a particular process stream are critical to the operation of the unit. Continuous chemical reactions require precise measurements to ensure that all of the reactants or raw materials are combined in the proper proportions to form the final products. Feed rates and product rates must be accurately controlled for economic reasons. Process flow measurements can be taken by any kind of flow meter, but flow control most often requires a flow transmitter. Flow transmitter. Certain types of flow meters, such as orifice plate meters as shown in picture and Venturi meters, use differential pressure to measure flow rate. Fluid flow through a pipe can be related to pressure differences inside the pipe when flow-restrictive devices, such as orifice plates, Venturi tubes, or flow nozzles, are installed. When the fluid flow encounters a restriction in a pipe, the pressure increases in front of the restriction. Fluid velocity through the restriction increases. The pressure on the other side of the restriction drops. A DP, differential pressure, cell is used to measure the difference between the pressure on the inlet and the pressure on the outlet side of the restricted device. The DP cell usually is connected to a transmitter that sends a signal to a controller. Controllers send signals to control valves to open or close depending on the comparison of the signal from the field with the flow rate set point. Positive displacement meters. There are two types of positive displacement meters, nutating disc and oval gear. The nutating disc meter is composed of a counter. A nutating disc resembles a spinning top, flow inlet, and flow outlet as shown in picture. Nutating disc meters measure fluid flow directly by counting the rotations of the disc as fluid passes through it. An oval gear meter has an internal structure that resembles that of a lobe pump as shown in picture. The lobe-shaped elements rotate as fluid passes through the internal chamber. The rotation of the gears is used to calculate the total flow rate. Rotometer. Another type of flow measuring device is a rotometer. A rotometer is composed of a tapered tube, scale, ball, or float, and inlet and outlet as shown in picture. During operation, flow enters a tapered tube at the bottom of the rotometer and lifts the ball off its seat. The ball provides a constant restriction to the flow and corresponds to the flow rate on the scale that runs the length of the tube. The higher the flow rate, the higher the ball rises in the tube. Fluid flows around the ball and out the top of the rotometer. Turbine flow meter. Turbine flow meters usually consist of a section of pipe with a rotor mounted in the pipe and a sensor on the outside of the pipe. As fluid enters the turbine flow meter, the turbine blades begin to rotate as shown in picture. The speed of the rotation is proportional to the velocity of the fluid. It is important to understand that flow velocity and flow rate are not the same. Flow velocity is the actual speed of the fluid, measured as distance per unit time, for example, feet per second. Flow rate is the total quantity of liquid that passes a specific point, measured as volume per unit time, for example, gallons per minute. Turbine flow meters are accurate over a wide range of flows. Weir and flume flow measuring devices. Weir and flume flow and level measuring devices are used to calculate flows in open channels as shown in picture. When a weir or a dam is placed into a process stream, it creates a restriction that forces the level to build. This level is used in a calculation to identify the flow rate. There is a direct correlation between the liquid level and the flow rate. The lower the level, the slower the flow. Flumes operate under the same principles as a weir but are used for higher flows. The flume is a narrow, sloping pass that funnels flow. At the inlet of the flume, the water level rises and is measured by a level measuring instrument that converts the level to a flow signal. Magnetic flow meters. Magnetic flow meters measure flow velocity based on the voltage created by the fluid flowing through a magnetic field. This type of meter is very effective for toxic or corrosive fluids because the fluid stream does not contact the measurement device. Ultrasonic flow meters. Ultrasonic flow meters measure flow rate based on the Doppler effect. A sound wave is transmitted to the fluid at a certain frequency. The frequency of the return sound wave will vary with the fluid velocity. Ultrasonic meters are not suited for clean fluids because they require some type of particle to reflect the sound wave. Vortex flow meters. Vortex flow meters measure flow rate by creating and measuring vortices in a flow stream. The vortices are created by a blunt object in the flow path called a strut bar. Thermal flow meters. Thermal flow meters measure flow rate based on changes in resistance due to changes in temperature. Thermistors are used to measure the change in resistance. Thermal flow meters are sensitive to the thermal conductivity of the fluid and are usually designed for a specific flowing material. The Coriolis meter. The Coriolis meter is a true mass flow meter that uses a vibrating U-tube to measure changes in momentum or mass flow rate. This type of meter is very effective for precise measurements of mass flow rate. Flow control loop. Flow control loops as shown in picture are typically designed so a measurement of the flow rate is taken first and then the flow is interrupted or controlled downstream. Flow controlled loops start at the primary element, which could be an orifice plate, venturi tube, flow nozzle, nutating disc, oval gear, or turbine meter. The most common primary element is the orifice plate. Orifice plates create a pressure differential that can be measured by a DP transmitter. Primary elements are typically used in conjunction with a transmitter. Although it appears that the primary element is interrupting the flow, it is not. Increased velocity across the orifice plate compensates for the restriction. The transmitted signal is sent to a controller that compares the incoming signal with the desired set point. If a change is required, the controller will send a signal to a final control element. Level measurement. Process technicians use fixed reference points, typically vessel taps, on which to base level measurements. The lowermost tap represents 0 level, and the uppermost tap is 100%. Correct level readings and control help make modern processing possible and profitable. Level measurements can be continuous, that is, levels monitored continuously, or single point. In single point measurements, readings are taken from a single point or from multiple points on a vessel. Single point measurements are used to turn equipment like valves, pumps, compressors, motors, alarms on or off and to detect high and low process levels. Level measurement devices can also be classified as direct or indirect. Direct level measurement instruments. Direct instrumentation is in physical contact with the surface of the fluid. Direct level measurement equipment may calculate the product surface level from a specific point of reference. Direct instruments include sight glasses, floats, displacers, and probes. A sight glass is a transparent tube with graduated markings, a gauge, mounted on the side of a tank as shown in picture. In a float and tape device, a float rests on the surface of the fluid, and the tape moves up and down, depending on the level. Displacers are buoyancy devices, or weights, that can be linked to a transmitter to control flow as shown in picture. Conductivity probes are high and low-level alarms. They use electricity to complete the lower leg circuit. If liquid reaches the higher leg, the circuit is broken. This type of system, which is designed to keep the level between the high and low conductivity probes, typically is used for non-flammable material. Capacitance probes are radiation devices or load cells. Indirect level measurement. Indirect instrumentation incorporates pressure changes that respond proportionally to level changes. DP cells convert pressure differences to a level indication. They measure the hydrostatic pressure difference between 2 points on a pressurized vessel. A continuous level detector gauge is a pressure-sensitive instrument that measures hydrostatic pressure in open vessels and converts it to a level indication. A bubbler system is a level measurement device that forces air through a tube that is positioned in the liquid. The liquid's resistance to flow registers on a pressure-sensitive level gauge that converts the pressure to a level indication. Bubbler systems are used to measure levels in open vessels. Level control loop. A typical level control system uses a primary element sensing device, direct or indirect, level transmitter, controller, transducer, and control valve. Level control loops use floats, displacers, or differential pressure transmitters. This picture uses a DP cell to detect level changes. The primary element or sensor is inside the transmitter, as indicated by the lack of a line separating LE and LT. These two devices couple up to detect and send a signal to a level controller. A transducer converts the signal and opens or closes the control valve. Basic elements of a control loop. The key component of automatic control is the control loop, the group of instruments that work together to control a process. As we have seen, these instruments typically include a transmitter coupled with a sensing device or primary element, a controller, a transducer, and a control valve. Process plants contain many control loops that are used to maintain pressure, temperature, flow, level, and composition. The basic elements of a control loop are: 1. Measurement device, primary elements and sensors shown in table. 2. Transmitter, a device designed to convert a measurement into a signal. This signal will be transmitted to another instrument. 3. Controller, a device designed to compare a signal with a set point and transmit a signal to a final control element. 4. Transducer, a device designed to convert an air signal to an electric signal to a pneumatic signal. Sometimes referred to as an I to P or as a converter. 5. Final control element, that part of a control loop, for example, control valve, damper, or governor for speed control, that actually makes the change to the process. The final control element is governed by a controller. This picture is an example of a cascaded control loop. Transmitters. DP cell transmitters can be found in two basic designs, pneumatic and electronic. Controllers are typically mounted between 400 closed loop and 1000 open loop feet from the transmitter. The signal from an electronic transmitter is proportional to the pressure difference between the high-pressure leg and the low-pressure leg. Standard output signals are 4 to 20 milliamps, 10 to 50 milliamps, and 1 to 5 volts. The 10 to 50 milliamps transmitter is used because it has a higher tolerance to outside interference than does the 4 to 20 milliamps transmitter. Pneumatic transmitters require a 20 to 30 psi air supply in order to run the standard 3 to 15 psi output. DP cells as shown in picture function by running a high and low pressure tap to each side of an internal twin diaphragm capsule. Pressure changes cause the diaphragms to move. This process increases or decreases the signal to the controller. Smart transmitters are another type of transmitter frequently found in the chemical processing industry. This type of transmitter is very reliable and does not need constant attention. Smart transmitters have an internal diagnostic system that warns the operator if a problem is about to occur. This type of transmitter can be used in liquid or gas service to control pressure, viscosity, temperature, flow, and level. Several advantageous features of the smart transmitter are speed, reliability, internal diagnostics, strong digital signal, and remote calibration capabilities. Controllers and controller modes. The primary purpose of a controller as shown in picture is to receive a signal from a transmitter, compare this signal with a set point, and adjust the process, that is, the final control element, to stay within the range of the set point. Controllers come in three basic designs: pneumatic, electronic, and digital. Electronic controllers were first introduced in the early 1960s. Before then, only pneumatic controllers were available. Pneumatic controllers require a clean air supply pressure of 20 to 30 psi. Several of the more attractive features of electronic controllers are the reduction of lag time in process changes, low installation expense, and ease of installation. With the widespread use of the PC or personal computer, several applications were found for controller use. Distributed control systems, DCS, software in computers replaced pneumatic and electronic controllers. The primary reason was the ease with which a DCS could be installed and the relatively few wires required to do it. Most modern plants include a combination of all three systems: pneumatic, electronic, and digital. The diagram of a control loop will identify the type of controller: pneumatic, electronic, or DCS. For example, in picture, the diagonal lines between the transducer and the valve signify pneumatic control. Controllers can be operated in manual, automatic, or cascaded or remote control. During plant startup, the controller is typically placed in the manual position until the process has lined out. In manual control, the controller sends an output to the final control element, as set by the operator. After the process is stable, the operator places the controller in automatic and allows the controller to supervise the control loop function. At this point, the controller will attempt to open and close the control valve to maintain the set point. Cascade control as shown in picture is a term used to describe how a second controller will reset a controller's set point in order to achieve a desired outcome. Proportional band. The proportional band on a controller describes the scaling factor used to take a controller from 0% to 100% output. If the proportional band is set at 50% and the amount of lift the final control element, globe valve, has off the seat is 4 inches, the control valve will open 2 inches. Range is defined as the portion of the process controlled by the controller. For example, the temperature range for a controller may be limited to 80 to 140 degrees Fahrenheit. Span is the difference, delta, between the upper and lower range limits. This value is always recorded as a single number. For example, the difference between 80 and 140 is 60 as shown in picture. Controller modes. Process technicians use a number of controller modes. The most common types are gain, reset, and rate. Gain may be used individually or in combination with reset or rate. Gain is most frequently paired with reset. Rate is typically applied to temperature control applications. The most advanced system uses a combination of gain, reset, and rate. Proportional control is primarily used to provide gain where little or no load change typically occurs in the process. Gain plus reset is used to eliminate offset between the set point and process variables. Gain works best where large changes occur slowly. Gain plus rate is designed to correct fast-changing errors and to prevent overshooting the set point. It works best when frequent small changes are required. Gain plus reset plus rate is applied where massive rapid load changes occur. Gain, reset, and rate combine to reduce swinging between the process variable and the set point. Gain. Most modern controllers use the term gain as a tuning constant. The gain is simply the ratio of the output signal from the controller to the error signal, difference between the process variable and set point. The gain is the reciprocal of the proportional band, PB. For example, if the PB is 100%, the gain equals 1.0. If the PB is 200%, the gain is 0.5 or 1/2. Gain is rarely used alone, because it can provide only a ratio response to a process change. Reset, integral. Reset is a control mode that responds to a process change by calculating a slope, in repeats per minute, back toward the set point. Reset is designed to reduce the difference between the set point and process variable by adjusting the controller's output continuously until the offset is eliminated. The reset mode responds proportionally to the size of the error, the length of time that it lasts, and the reset gain setting is shown in picture. Rate derivative. Rate mode enhances controller output by increasing the output in relationship to the changing process variable. As the process variable approaches the set point, the rate relaxes, providing a braking action that prevents overshooting the set point. The rate responds aggressively to rapid changes and passively to smaller changes in the process variable as shown in picture. Final control elements. Automatic valves. Final control elements typically are automatic valves, but motors or other electric devices can be used. The final control element is the last link in the control loop and is the device that actually makes the change in the process. Automatic valves will open or close to regulate the process. Because they can be controlled from remote locations, they are invaluable in modern processing. An actuator is the device that automates a valve. The actuator controls the position of the flow control element by moving and controlling the position of the valve stem. Actuators come in three basic designs: pneumatic, electric, and hydraulic. Pneumatic or air-operated actuators are the most common. Pneumatic actuators convert air pressure to mechanical energy. They can be found in three designs: diaphragm, piston, and vane. The diaphragm actuator is a dome-shaped device that has a flexible diaphragm running through the center. It is typically mounted on the top of the valve. The center of the diaphragm in the dome is attached to the stem. The valve position, on or off, is held in place by a powerful spring. When air enters the dome on one side of the flexible diaphragm, it opens, closes, or throttles the valve, depending on design. The piston actuator uses an airtight cylinder and piston to move or position the stem. It is commonly found in use with automated gate valves or slide valves. It is used where a lot of stem travel is needed. Vane actuators direct air against paddles or vanes. Electrically operated actuators convert electricity to mechanical energy. There are two types: solenoid valve and motor-driven actuator. Solenoid valves are designed for on-off service. The internal structure of a solenoid resembles a globe valve. The disc rests in the seat, stopping flow. The stem is attached to a metal core or armature that is held in place by a spring. A wire coil surrounds the upper spring and stem. When the wire coil is energized, a magnetic field is set up, causing the armature to lift and compressing the spring. The armature is held in place until the current stops. A motor-driven actuator is attached to the stem of a valve by a set of gears. Gear movement controls the position of the stem. Hydraulically operated actuators convert liquid pressure to mechanical energy. The hydraulic actuator uses a liquid-tight cylinder and piston to move or position the stem. It is commonly found in use with automated gate valves or slide valves and is used where a lot of stem travel is needed. The following expressions are used commonly to describe actuators. Air to open, spring to close. Fails in the closed position if air system goes down. Air line is typically located on the bottom of the dome. Air to close, spring to open. Fails in the open position if air system goes down. Air line is typically located on the top of the dome. Double acting, no spring. Air lines located on both sides of the dome. Fails in last position. Air pressure to diaphragm is locked on instrument air failure. The most common type of automatic valve is a globe valve because of its versatile on-off or throttling feature. Control loops use on-off or throttling type valves to regulate the flow of fluid into and out of a system. In addition to the pneumatic, electric, and automatic control valves, there are also spring or weight-operated valves. Spring-operated valves hold the flow control element in place until pressure from under the disc grows strong enough to lift the element from the seat. A check valve would be in this category. Interlocks and permissives. An interlock is a device designed to prevent damage to equipment and personnel by stopping or preventing the start of certain equipment if a preset condition has not been met. There are two types of interlocks, soft wire and hard wire. Soft wire interlocks are contained within the logic of a programmable computer. Hardwire interlocks are a physical arrangement. The hardwire interlock usually involves electrical relays that operate independently of the control computer. In many cases, they run side by side with the computer softwire interlocks. However, hardwire interlocks cannot be bypassed. They must be satisfied before the process they are part of can take place. A permissive is a special type of interlock that controls a set of conditions that must be satisfied before a piece of equipment can be started. Permissives deal with startup items, whereas hardwire interlocks deal with shutdown items. A permissive is an interlock controlled by the DCS. This type of interlock will not necessarily shut down the equipment if one or more of its conditions are not met. It will, however, keep the equipment from starting up. Manual and automatic control. During a unit startup, console operators will use manual control to initially establish a steady state flow through the system. Typically, when a new process is being brought online, a control loop will swing high and low as it attempts to match the set point. Experienced technicians are familiar with the operating valve percentage that is established when a unit is lined out. By placing the valve in manual control, process variations are reduced. Once the system is online, the console technician will insert the set point on the controller and place it in auto. This procedure enhances the time it takes to bring a unit up to steady state and produce a high-quality product. Automatic control uses all 5 elements of the control loop in a dynamic system that measures, compares, and attempts to control a specific process. Process units may have hundreds of control loops that make it possible to control level, pressure, temperature, flow, and a variety of analytical processes. Automatic control allows a process technician to control a much larger and more complex arrangement of process systems. Cascaded control. Cascade control uses elements from 2 separate control loops. One of the controllers functions as the primary controller, and the other functions as the secondary controller. This relationship is often referred to as master-slave control. This picture illustrates the basic elements of a cascaded system. It is important to point out that in this type of process control, controllers will communicate only with other controllers. In many process systems, it is possible to accomplish a variety of similar objectives simultaneously. For example, in a distillation system, reflux is used to control temperature and improve product purity. In most cases, a flow control loop is used to ensure steady flow. However, temperature control is considered to be the single most important factor in this system. When a temperature element is placed on the top tray and connected to a transmitter, controller, transducer, and control valve on the reflux line, a conflict appears to exist between the flow control valve and the temperature control valve. By selecting the temperature to be the primary controller, one can allow both the flow control and temperature control to work together to accomplish operational objectives. Analytical control. An analytical control loop is used to control process variables such as pH, ppm, and product concentrations. This picture provides an example of how one of these systems may appear. Cooling towers require close control of pH and parts per million, ppm. Shifts in these variables can cause serious problems. Control systems can be used to control these analytical variables. Automation enhances the ability of a process operator to control large and complex process networks. The basic instruments include gauges like pressure, level, temperature, and flow, differential pressure, DP, cells, transmitters like pressure, level, temperature, and flow, controllers, pneumatic and electronic, transducers, control valves, and primary elements and sensors, displacer and buoyancy float, thermocouples, orifice plates, etc., and computers. The most common type of pressure element is a Borden tube. There are three commonly used pressure scales in the manufacturing environment: gauge scale, PSIG, absolute scale, PSIA, and vacuum scale, mercury. Process flow measurements frequently are taken by one of the following devices: a flow transmitter, nutating disk meter, oval gear meter, rotometer, turbine flow meter, weir, and flume. Level measurements are identified by a fixed reference point, typically 0, above or below a product. Level measurement devices can be classified as direct or indirect. Direct instrumentation is in physical contact with the surface of the fluid. Indirect instrumentation incorporates pressure changes that respond proportionally to level changes. A control loop is a group of instruments that work together to control a process. These instruments typically include a transmitter coupled with a sensing device or primary element, a controller, a transducer, and a control valve. The controller receives a signal from a transmitter, compares this signal with a set point, and adjusts the final control element, process to stay within the range of the set point. Controllers come in three basic designs: pneumatic, electronic, and digital. Final control elements are typically classified as automated valves, but motors or other electrical devices can be used. The final control element is the last link in the modern control loop and is the device that actually makes the change in the process. An interlock is a device designed to prevent damage to equipment and personnel by stopping or preventing the start of certain equipment if a preset condition has not been met. A permissive is a special type of interlock that controls a set of conditions that must be satisfied before a piece of equipment can be started. Permissives deal with startup items, whereas hardwire interlocks deal with shutdown items. That's all, gentlemen. If you like my training course, please follow my YouTube channel Petro Intelligence for more courses. Good day and good luck.